Now we do again the calculation, minimizing the amount of iron. Look on the two red boxes on the bottom left, which highlight the selection of the minimum iron as a target for optimization. Now the quantity of iron in the chemical composition is gone down to 0. The result of the minimization of the iron oxide raised the cost up to 429.6, which is still lower than the cost of the original formulation with 0.077 of iron. Let's do the opposite. Now we give as a target for the optimization the maximum amount of iron. The amount of iron in the chemical composition goes up to the upper limit of the allowable constraint, 0.2. This is the batch with maximum amount of iron with a cost of 409.49. This cost cannot be lower than the result obtained as a minimum cost. All these calculations, which yield the same chemical composition with different raw material, take only few seconds. There is no way to do the same by manual calculation. It will take a lifetime and it will never be as accurate as this. In the chemical composition, there may be a little amount of oxide which were not present in the original composition. This is possible because in this case the function which allows the use of non-specified oxide is enabled. Since there is a little tolerance between the maximum and the minimum quantity, there is a little room to accept unspecified oxide, finding a solution that satisfies all the constraints and that can give an advantage on the cost. Of course, it is possible to disable this function, and in this case the final composition will contain only the elements specified in the starting composition. Glaze Master can be used to calculate the mineralogical composition of the raw materials. Let's see how it works. We load on the left the raw material, and on the right we have the chemical composition. Note that the loss of ignition, highlighted with a red box on the bottom of the left page, is 5.24. Now we bring the chemical composition of the raw material on the left and select the list of the standard minerals as raw material for the batch reformulation. Glaze Master can be supplied with a database of standard minerals, which can be updated by the user. Here we can see the list of the standard minerals that will be used for the calculation. On the bottom left, we enable the function which enables the use of the loss of ignition as a constraint for the reformulation. This is the result, and we can see on the column of the loss of ignition that the value match the constraint that we have set. Of course, it is advisable to use X-ray diffraction to know which minerals are actually present, and using Glaze Master we can calculate the percentages of raw material that will perfectly match the chemical composition and the loss of ignition. Now we can check that the calculated chemical composition matches the input composition. As we can see, the result also contains water, because two of the standard minerals that have been used do contain water. This water, as all the other volatile elements, is not included in the addition of the oxides, which ends to 100, but it is always above 100. Now we use the second calculation program, starting directly from the input of a chemical composition. This is the input of a chemical composition of a target glass, and we use the default option for the minimization of the fired cost. Now we select a list of raw material to be used and start the calculation with the function highlighted by the red box enabled. This is the result of the function which creates a table with all the raw materials made available for the calculation. This is the result of the calculation. The titanium oxide has reached the maximum constraint, and it is highlighted in Bordeaux. On the third page of the results, we can see the contribution of each raw material to the final composition and identify the reason why the titanium oxide has reached the maximum. On the fourth page of the results, we can see the contribution of each oxide to the properties of the glass, like thermal expansion, surface tension, and index of refraction. Now we see a short example of the third calculation program. This calculation sheet does the calculation only on the chemical composition. In this case, we select the input as molar percentage. Here we input the molar ratio. In this example, 1 mole of silica, 1 mole of boron, and 1 mole of lead oxide. At the end of the input, the composition is converted into the other formats, by weight, by moles, in Seeger formula, or by atoms. Now we can transfer this result to the second calculation program to exact a raw material formulation which matches this composition. This is done by clicking on the reformulation button. Here we transfer the composition in the optimization program. Then we selected all the available raw material and use the default option of minimization of the fired cost. This is the result of the optimization. From all the available raw materials, only 4 were used. In the red column we get the raw batch, while in the green column we get the quantity which will yield 100 kg of product.